So our final speaker for the conference is Alex Margolis, who's going to talk to us a bit about model geometries dominated by locally finite graphs.
So firstly, thanks, Frank, for inviting me, and also because I'm the last speaker, on behalf of all of the participants and speakers, we'd like to thank the organizers. So thank you very much, including the ones that aren't here. So I'm going to be talking about model geometries dominated by locally finite graphs. And first, I should say what some of those words mean. Firstly, a bit about the sort of general sort of theme of the talk. So in geometric group theory, you want to study a finitely generated group via its actions on metric spaces and use algebraic properties about the group to deduce geometric properties about space in which it acts, and vice versa. And this talk is very much in that theme. And the nicest sorts of spaces on which a group can act are what are called model geometries. So I want to make sure everyone understands exactly what I mean by this. So it's model geometry of a finitely generated group is a proper metric space X admitting a co-compact proper isometric action of that group gamma. So proper, again, means closed balls are compact. Co-compact means there's some compact subset of the space such that if you take translates of this compact subset by gamma, you get the whole space. And proper actions are where if you, for any compact subset of the space, there are only finitely many translates of that subset that intersect itself. Okay, and some key examples to think about. If we have a closed hyperbolic surface, then the hyperbolic plane is a model geometry of the fundamental group of that surface. And another example is very general. If we have any finitely generated group with finite generating set S, and we take the Cayley graph with respect to that finite generating set, then we again get a model geometry. So any Cayley graph can be a model geometry, and the hyperbolic plane and more general symmetric spaces as well. And these two spaces are very different sorts of things. So the Cayley graph is a locally finite graph. And if you look at the automorphism group of that graph or the isometry group of that graph, that will have discrete orbits because it sends vertices to vertices. Whereas if you look at the hyperbolic plane and you look at the full isometry group of the hyperbolic plane, then this will be some virtually connected Lie group. It will be uncountable and it will act transitively on the space. So for any 2 points in H2, there's an isometry that takes 1 point to another point. And so these are very different sorts of metric spaces. And so the goal of this talk is to understand to what extent finitely generated groups can have model geometries that look a bit more like H2 and aren't just graphs, aren't just the Cayley graphs of the group, essentially. So to make this precise, we have to talk about the notion of domination of metric spaces, which I will define. So first thing to say is that if we have a proper metric space, then the isometry group of that space you can think of as a locally compact topological group when you equip it with the compact open topology or equivalently the topology of pointwise convergence. And throughout this talk, when I talk about isom X, I'm going to assume it's a topological group in this way. And if we have two model geometries, X and Y, we say X is dominated by Y. If there's a map phi between the isometry groups from isom X to isom Y, which is firstly continuous, secondly is proper, so that means inverse images of compact sets are compact, and thirdly has compact image. And in the special case where isom X and isom Y are actually discrete, then this is going to be a homomorphism with finite kernel and with finite index image. So it's an isomorphism up to finite error. And because we're working with possibly non-discrete topological groups, you can think of phi as an isomorphism up to compact error. And if you haven't thought about topological groups much, the sort of slogan, which I will justify in a little bit, is that if X is dominated by Y, then we think of Y as being more symmetric or possibly just as symmetric as X is. So why is this? So if take the space X here that I've drawn here, we've got a picture of it, and we think of this as a flat torus equipped with a flat metric, where we attach two antennae to a point. So we have these unit length intervals that we stick on one point of the space. And then we take the universal cover of this space, and we get a grid, a copy of the Euclidean plane, where every point on the integer lattice, we have these two antennae attached. We have these unit length intervals. And now we're going to consider the full isometry group of X tilde. And the key thing is that this has a non-discrete isometry group, because you can have isometries of X tilde that, for instance, fix L tilde, but that can arbitrarily switch the two antennae attached to a point. And those are quite boring isometries. They don't do anything interesting. And in fact, all of these isometries lie inside some compact normal subgroup in the full isometry group. And we have a map phi from isom X tilde to isom E squared, which just forgets about what happens to the antenna and just restricts the isometry to what it does on the Euclidean plane. And this map phi is satisfies the conditions in the definition of domination. And the idea is you think of this map phi as forgetting about all of the compact noise in isom X tilde. You're forgetting about all the isometries that fix the Euclidean plane and just commute, sort of flap some of the antennae you've attached by quotienting out by this compact normal subgroup. And you include it in the full isometry group of the Euclidean plane, which is much bigger. It's an uncountable group, but it has a lot more interesting isometries that can't be seen from X tilde, because there are lots of isometries of the Euclidean plane that don't preserve the lattice. So that's the general idea. We get rid of boring isometries and we gain lots of interesting isometries. And so this space X tilde is an example of a space that's dominated by the Euclidean plane. And the main question, the main problem that this talk will solve is classifying precisely which finitely generated groups have the property that all model geometries of that finitely generated group are dominated by a locally finite graph. Okay, and we've already seen some model geometries, the hyperbolic plane and the Euclidean plane, and I claim that these are not dominated by locally finite graphs. There are isometries of these spaces that can't come from isometries of some locally finite graph. And the way of seeing this is quite sort of a powerful way to study these sorts of questions. You look at the topology of the isometry group, and this is a criterion that tells you the isometry group of some model geometry is dominated by a locally finite graph, if and only if the isometry group is compact by totally disconnected. And I will very briefly talk about some of the ideas in the proof of this. So one direction, both directions are fairly straightforward, but the easier direction is the observation that if we have a locally finite graph that dominates the space X, then because the automorphism group of that space is a locally finite graph is totally disconnected, we have a homomorphism to a totally disconnected group, and that tells you you're dominated by, well, that gives you one direction of the proposition. And the other direction, which is a little bit harder, but still not too hard, if the full isometry group is compact by totally disconnected, then there's always a way of producing some locally finite graph, namely the Cayley-Abels graph, it's called, of I sum x, which dominates x. So if you have this topological property of the isometry group, then you're dominated by a locally finite graph. So this gives a powerful criterion for telling when you are or not dominated by a locally finite graph. So what we're now going to do to see this problem is interesting, and we have lots of spaces where we have some sorts of continuous behavior, a bit like the hyperbolic plane, where we have transitive orbits, and some directions where we have discrete orbits. We're going to see an example of a group with mixed sort of behavior. You'll see what this means in a minute. The Baumslag-Solitar group BS12. So that's a group with this presentation generated by A and T with one relator T inverse is equal to A squared. And I've drawn here a portion of the Cayley complex of this group. And you can see the horizontal arrows going to the left correspond to the generator A. And so moving one step to the left is multiplying by A, and moving one step down is multiplying by T. And you can see that this is you can sort of see the defining relation T inverse is equal to A squared in this Cayley complex by tracing, if you go here, if you go down one, then across one, and then up one, that's T inverse. And what you've done is move 2 to the left. You move 2 steps to the left. That means you multiplied by A twice. And so you see that T inverse is equal to A squared. And we want to give this metric in the following way. So for every horizontal strip between 2 of these lines with red arrows on it, we want to give it a strip so that it's isometric to a region in the hyperbolic plane between 2 concentric horocircles. And we could do this in a way so that every edge labeled by a red arrow has the same length. And if we do it in this way, then the group will act isometrically on this space. Okay. And I claim that this space X is not dominated by a locally finite graph. And the way to see this is to apply the previous proposition, namely to show that the full isometry group of this complex we've constructed is not totally disconnected, or not compact by totally disconnected. And the idea is that there's a continuous one parameter family of isometries you can have in this space. Namely, you can just do arbitrarily small translations to the left or right, sort of in the horizontal direction, while fixing the tree direction of this Cayley complex. Okay, so the Cayley complex topologically looks like a tree times the real line, and by doing translations in the real line direction, we can get a continuous one parameter family of isometries. And so the isometry group is neither totally disconnected nor virtually connected. So this is something that it's not dominated by a sort of nice classically studied space like a symmetric space, like the hyperbolic plane, for instance, nor is it dominated by a locally finite graph. And what we want to do now is to analyze the algebraic properties of this group and see how we can characterize the full class of groups that admit model geometries like this, where there's some direction where we have continuous one parameter subgroups, or alternatively, when there's when the space isn't dominated by a locally finite graph. Okay, so we say a subgroup lambda is commensurated if when we intersect lambda with one of its conjugates, that has a finite index in lambda. And we want to do this for every possible conjugate of lambda. And if that's satisfied, we say the subgroup is commensurated. And this property will capture lots of the behavior of space of finitely generated groups that have some model geometry not dominated by a locally finite graph. So let's see some examples of this. So firstly, if lambda is actually a normal subgroup, then it's going to be commensurated. Why is that? Because if you conjugate, if you take any conjugate of lambda, it's actually equal to lambda, and so clearly it has finite index subgroup in lambda. If we take the group BS12, that's a group with this presentation, and we take the infinite cyclic subgroup generated by A, then we can see that this is commensurated, but it's very far from being normal. And again, the way of seeing this is using the defining relation. If you conjugate A by T, you get A squared. If you conjugate it by the nth power of T, you get A to the 2 to the n. So if you conjugate by larger and larger powers, you get deeper and deeper finite index subgroups of A. That's the idea. So this is a subgroup which is commensurated, but is very far from being normal and can't even be made normal by passing to finite index subgroups or anything like that. And another example, which again motivates some of the ideas that go into the theorem, the main theorem I'm going to talk about. If we have a locally compactly generated group, and we have a compact open subgroup, then that subgroup is always commensurated. And this is fairly easy to see. It's an elementary topological argument. You play the compact and the open properties against each other and you cover cosets of A. You show that every conjugate of H is covered by finitely many cosets of H, and that gives you that H is commensurated. And finally, this is in some sense a universal example. If we have a group that acts on a connected locally finite graph X, and we take a vertex of X, then the stabilizer of that vertex is always a commensurated subgroup of the big group. Okay, and the reason I said this is universal is because whenever you have a finitely generated group, which contains a commensurated subgroup, you can always find some connected locally finite graph on which the ambient group acts and on which the subgroup is the stabilizer of a vertex. Okay. And the main theorem, we're getting close to being able to state it, but we're not quite there yet. We need a sort of technical refinement of the notion of a commensurated subgroup, namely something that's called a uniformly commensurated subgroup. And to motivate the idea, I just want to say that if you have a normal subgroup, lambda, of a group gamma, then you can, the group gamma acts on conjugation by lambda, and that gives you a homomorphism from gamma to the automorphism group of lambda. And there's a nice analog of this. If you have a commensurated subgroup, then gamma doesn't act on lambda by conjugation, but it acts on sufficiently deep finite index subgroups of lambda by conjugation. And so we get a map homomorphism from gamma to what's called the abstract commensurator of lambda. So this is an analog of the map from gamma to the automorphism group of lambda when lambda is normal. And the abstract commensurator group is a group of equivalence classes of isomorphisms between finite index subgroups. And for instance, the easiest example of a non-trivial example of an abstract commensurator is the abstract commensurator of z to the n is glnq. And if lambda is finitely generated, then there's a natural way of mapping the abstract commensurator into the full quasi-isometry group of lambda. So this is the group of all self-quasi-isometries of lambda up to an equivalence relation, where two quasi-isometries are equivalent if they're close. And now we can state this definition of what it means to be uniformly commensurated. So if we have a finitely generated commensurated subgroup lambda of gamma, we say that it's uniformly commensurated if, as well as being commensurated, the image of the map, so we have a map from gamma to the abstract commensurator of lambda, and then we post-compose that with the inclusion into the quasi-isometry group. We want the image of this to be what's called a uniform subgroup of the quasi-symmetry group. And that means essentially that every element in the image can be represented by quasi-symmetry whose constants are uniformly bounded. And again, this is, if you haven't thought about these things before, this definition might not make too much sense. So I'll give a few examples of what to have in mind. So firstly, if lambda is actually a central subgroup, then the action of gamma on lambda by conjugation is trivial. So that means lambda is uniformly commensurated. If we have the infinite cyclic subgroup of the group BS12 that we talked about earlier, this is a commensurated subgroup that's not uniformly commensurated. And I already explained the sort of geometric idea behind it. The idea is if you conjugate A by a large power of T, that corresponds to a quasi-symmetry that expands or contracts A by a very large amount. And by taking a sufficiently large power of T, you can get quasi-symmetry constants that are arbitrarily large. So this is a group that's not uniformly commensurated. Another nice class of examples that are always uniformly commensurated is if lambda is a commensurated subgroup which satisfies Mostar rigidity, then it's always uniformly commensurated. And the idea behind this is quite natural if you know what Mostar rigidity is. The idea is that every abstract isomorphism between any finite index subgroups of lambda has to correspond or be induced by, in some sense, an isometry of an associated symmetric space. And because it comes from an isometry, the quasi-isometry constants are sort of uniformly bounded. And finally, another non-example, if we have a closed hyperbolic surface and we have a pseudo-Anosov homeomorphism, and then we look at the fundamental group of the mapping torus associated to this map F, then we get the surface group extension of pi1s by Z, and the action of F on pi1s distorts everything by a lot. And so if we take larger and larger powers of F, we get worse and worse quasi-isometry constants. So this is a normal subgroup, therefore a commensurated subgroup that's not uniformly commensurated. Okay, and now we can come to the punchline. Using all of these terms, we can give a precise answer to the problem I stated earlier in the talk. A finely generated group gamma has a model geometry which is not dominated by a locally finite graph, precisely when the following holds. So gamma contains an infinite commensurated subgroup lambda, such that one of the following two things holds. First thing, lambda's a finite rank free abelian group. There are no extra conditions. And the second condition is lambda is a uniformly commensurated subgroup and is a lattice in a connected center-free semi-simple Lie group, modulo possibly quotienting out by some finite kernel. Okay, so this gives a very precise answer to the question. And I should mention that if lambda is commensurated and satisfies Mostar rigidity, which is the case for most of the groups in part 2 of the theorem, then it's automatically uniformly commensurated. So part 2 is really only there to rule out surface groups and things that split as direct products virtually, where some of the factors are surface groups. That's the only case where you need the uniformly commensurated hypothesis. And another way of formulating the main problem is you can ask which finitely generated groups embed as what's called the uniform lattice in a locally compact group. And this theorem gives a complete characterization to this question. It tells you precisely which groups embed as uniform lattices in locally compact groups, which are not compact by totally disconnected. And this is really just a reformulation of what it means to not be dominated by a locally finite graph. And I'm almost out of time, but I want to give a nice corollary to the theorem. If we restrict to groups of cohomological dimension 2, we can interpret this class of groups a little bit more precisely. So such a finitely generated group of cohomological dimension 2 has a model geometry not dominated by a locally finite graph, precisely when it's either a surface group, the fundamental group of a closed surface of non-positive Euler characteristic, or it's what's called a generalized Baumslag-Solitar group, which I've given the definition up at the top, but it generalizes Baumslag-Solitar groups we talked about earlier, and these are groups that have a similar geometric and algebraic structure to Baumslag-Solitar groups. Well, thanks very much for listening. If you have any questions.
Great. Thank you, Alex. Does anyone have any questions from the audience? Please unmute yourself if you do. If not, let's thank Alex again.